So, good afternoon. I'm Yijun from the University of Tokyo. Today, I'm gonna present paper Generative Melody Composition with Human-in-the-Loop Bayesian Optimization. I will start from our motivation. Humans are great at composing music for a long time. Nowadays, many research projects have tried to learn Latin space of deep music generative models such as GAN and VAE. When we sample Latin vectors on the smooth Latin space, even novice composers can quickly generate various meaningful melodies. However, novice users may face significant challenges when exploring the Latin space to find a desired melody, since the Latin space is often unintuitive and high dimensional. Thus, our motivation comes from it that we want to investigate how humans would steer the deep generative models to find their desired melody. So in the following, I would like to introduce some related works from two perspectives: tools for deep music generation and human-in-the-loop Bayesian optimization. I will start from the tools. So Music VAE, a generative melody model, has a smooth Latin space which allows users to sample and interpolate on it. Many applications powered by Magenta.js and Music VAE and other models have been developed which enhance the interaction between human and music. Our system used the pre-trained Music VAE model and considered its smooth Latin space. While we share a similar motivation, we focus on investigating the approach of formulating the task as a human-in-the-loop optimization. I will introduce the Bayesian optimization and human-in-the-loop Bayesian optimization in the next slides. So Bayesian optimization is a black box global optimization technique. It finds optimum using a smaller number of samplings. It chooses the next sampling point by maximizing the expected improvement. I won't spend too much time on introducing the standard Bayesian optimization. Please refer the Shahiri's paper if you are interested. So there are extended Bayesian optimization for human-in-the-loop sightings. This enables to handle the perceptual objective functions that require human assessment. Here's another image of the process. Bayesian optimization iteratively suggests candidates to the user based on their preference. So if you are interested in it, please refer to Koyama-san's paper for details. And these projects all take human-in-the-loop Bayesian optimization as the method to search for the desired solution according to the user's preference. Here, our question is same as the projects mentioned. Humans' preference is expensive to query. We also apply human-in-the-loop Bayesian optimization in our project. Our system used this method. Iteratively asks the user to compare multiple melody candidates sampled from a one-dimensional subspace and to select the preferred one. Please note that our 4 candidates sampled by Latin space interpolation between the current best candidate and a BO-generated candidate where the corresponding interpolation weights are 0.25, 0.5, 0.75, and 1.0. In the following, I would introduce our system design. Our system is a web-based application. The front end is implemented in JavaScript, while the back end is managed by a Python server. All the musical data represented on the interface and transferred before from the front end and back end are on the media level. We have 2 modes, composing mode and searching mode. We will have a demo to show the usage in the next slide. Here's the demo.
composing interface. Each column represents a 16th note duration. Each row represents a key on the piano from C3 to B5. The user can input notes into the system by left-clicking and dragging on the note sheet. Drag a note up and down to change its pitch. Click the Play button. The user can play the notes to check whether they are satisfied with them. Right-click a note to delete it. The user can add 2 more blank bars by clicking the Add button. Delete them by clicking the Delete button. When they are hindered by lack of ideas, they can start searching. Choose 2 bars and open the searching interface. In the first iteration, candidates are randomly and uniformly sampled on the dimension-reduced latent space of the pre-trained generating model. The 2 bars the user selected are shown in the editing region. We suppose the user prefer the melody in the editing region to the candidates. The user can play a candidate to hear how it sounds. If the user likes a candidate, they can click it to select it. The user can always go back to the initial state of the current iteration.
Okay, so that's it. I will introduce the algorithms behind and our implementations. So our implementation used the pre-trained music VAE model for melody generation, whose latent space is 512 dimensions. Its main structure contains an encoder and a decoder. We use this to encode the MIDI level melody to latent space and decode the latent vector to MIDI melody. However, 512 is too large, which means Bayesian optimization cannot work efficiently. Thus, we have the dimension reduction in our system. We tested several techniques for this purpose, including principal component analysis, autoencoders, and variational autoencoders. We found that variational autoencoders work well in terms of minimizing the reconstruction errors and generating convincing and various melodies. We also tested several different dimensionalities and found that reducing into a 4-dimensional latent space would be a reasonable choice. Note that this choice is consistent with the previous work called MIDI-Me. For the training, we selected 10 songs, so splitted them into 284 2-bar melody fragments from the music VAE training dataset, the genres of which cover pop, rock, country, and R&B. So this is the formulas. So in Formula 1, F represents the user's subjective preference over melodies, or how good the melody is. Z is the latent representation of the melody. The asterisk is the latent vector that generates the most satisfying melody. So the optimization target here is to find Z that maximizes the F. Note that we do not know the landscape of F, which is the challenge of this problem. The goal here is to solve this optimization problem by iteratively presenting candidate solutions to the user and asking them to choose preferred one. So in Formula 2, when user edits the melody selected, it means that its latent vector is preferred over the latent vector on the right hand. Here we'll show the evaluation of our algorithms. We conducted an experiment from the algorithm viewpoint where we artificially simulated the user behavior. The goal here is to verify whether our algorithm can find the desired melody in a reasonable number of iterations. We used SDTW as the metric, as the quantitative similarity metric between two melodies in melody space. We simulated user behaviors as follows. So first, we generated a desired melody by random sampling on the Latin space. Given the set of candidate melodies in the Tth iteration, we select the one with the smallest SDTW to the target as the best preferred one at this iteration. Then we got the candidates for the next iteration. We iterated this procedure for 50 times and performed 100 trials in total. Here's the result. In addition to the SDTW values, we also recorded the 4-dimensional Latin vectors of all the selected candidate melodies and calculated the Euclidean distance to the Latin vector of the desired melody. We could observe that the SDTW value decreased as the iteration went on, which was our expectation. We found Euclidean distances in the Latin space also decreased consistently. Well, this indicates the smoothness of the Latin space. The results suggested that Bayesian optimization could effectively find melodies that are reasonably similar to the target one after around 20 iterations in the 4th-dimensional Latin space. We also conducted an informal pilot study with 2 novice composers who had wishes to compose music but had no formal composition training. We asked one of the 2 participants, like A, to compose a 32-bar melody and B to compose a 16-bar. During the experiment, the participants were free to compose melodies by themselves or use the search function to get help from the system. When they used the search function, they were asked to go for at least 20 iterations. A finished composing within 2.5 hours. B finished it within 1.5 hours. In the experiment, A used the search function 8 times, while B used it 6 times. We'll show the results in the following slide. In the follow-up interview, both participants explicitly expressed that the system had effectively provided them more ideas than they had, which inspired their creativity. Both of the participants also mentioned that the system made the process of composition easier. Well, here's the composition result of our pilot study. I will only show the B's result here. If you're interested, you can visit the project homepage to watch them. So let's come to the conclusion. In this project, we demonstrated that human-in-the-loop Bayesian optimization had the potential to work effectively and efficiently on searching for the user's desired melody from the Latin melody space. We also showed that Bayesian optimization could suggest satisfying candidates within a reasonable number of iterations. The pilot study result suggested that it also inspired the user's creativity and lowered the learning barriers of novice composers. In the future, we plan to investigate how to apply Bayesian optimization to a higher dimensionality, for example, 512, efficiently and effectively in an interactive system. We also want to provide more control in terms of the searching behavior. Well, thanks for listening. So let's go into the question and answer round. Thank you.